Hello! In the previous video, we introduced the method of maximum likelihood. In that video, and the exercises that follows, we supposed that we had generated a series of Bernoulli random variables like the one shown here. We then tried to use this data to estimate the p-values for this random variable that had been generated multiple times. We argued that as all our data points are Bernoulli random variables, the sum of all the random variables is a binomial random variable with the probability mass function shown here. The problem of finding the p-parameter for the Bernoulli random variable we have sampled thus just reduces to the problem of finding the value of the parameter p in this expression. So what can we do to find the value of this parameter p given that we have this particular data? Well, let's first note that we can use the value that we know the value of capital X here because we did the experiment. Furthermore, we know that the probability that capital X is equal to small x is a probability, and that if for the particular value of x that we'd obtained in our experiments, the probability that capital X is equal to small x were small, then the model would be bad. If the probability that capital X is equal to small x was small, this would imply that it was very unlikely that we would get this result. But we did get this result in our experiment. What we therefore need to do is to adjust the value of the parameter p to make this probability, the probability that capital X equals small x, as large as it can possibly be. In other words, we want to adjust the parameter p so as to maximize the probability that capital X is equal to small x, the value that we got in the experiment. We know how to maximize a function, however. We simply take the first derivative of the function and set it equal to 0. In this case, we thus need to differentiate the probability that capital X equals small x with respect to the parameter p and set this equal to 0. When we do this differentiation for the function shown at the top of the slide, we find, after some manipulation, that the derivative with respect to the parameter small p is given by the following expression. Now, notice that the binomial coefficient is always greater than 0 and that p must be between 0 and 1. Consequently, this whole part outside the bracket cannot equal 0. It is the term inside the bracket that must be equal to 0 as shown here. If we multiply out the brackets in this expression, we find the following. We can cancel out the factors of xp and minus xp to get and then arrive at something simpler, which can be rearranged to give us that our estimator for the value of the parameter p is x, the result of our experiment, divided by n, the number of experiments we performed. This method for finding the p-parameter is known as maximum likelihood estimation. Through the exercises, you have seen that it can be generalized to other types of random variable. We've just seen how, if you perform a series of trials and count the number of times we got a 1, we can estimate the p-parameter by maximizing the likelihood of this result using the probability mass function for a binomial random variable. If, by contrast, we have the number of trials we have performed till we get a success, we are generating a geometric random variable. We can thus estimate the p-parameter of the underlying Bernoulli random variables by maximizing the likelihood for the particular outcome we observed under the assumption that it is geometrically distributed. Lastly, if we have measured the number of trials we have performed until we get our successes, then we have generated a negative binomial random variable. We can thus estimate the p-parameter for the underlying Bernoulli random variables by maximizing the likelihood for the particular outcome we have observed under the assumption that this outcome is a sample from a negative binomial random variable. This is all well and good and hopefully not too difficult once you've got the basic idea. The question you might be asking, however, is if we can use this technique of likelihood maximization if we are given other types of random variable. For example, if we have multiple binomial, geometric, or negative binomial random variables, can we determine the maximum likelihood estimators for the parameters? The answer to this question is, of course, yes. We can write the following expression for the likelihood of getting a particular set of results in n independent experiments. In this expression, the xi here is used to indicate the result from the ith experiment. The probability that capital X is equal to small xi is thus the probability of getting this particular result under the assumption that the result is distributed according to the probability distribution P. To account for the fact that we have done multiple independent experiments, we then take a product of the probabilities of all the results from all n experiments. We can write this product of probabilities using a product sign as shown here. The capital Pi here tells us to take the product of the numbers after it, just as the capital sigma tells us to take the sums of the terms after the summation sign. Just in case that is not clear, however, we can write out the product here explicitly as shown. This abstraction is all well and good, but to understand it better, let's see if we can use this idea to solve a real problem. Let's suppose that we have generated n binomial random variables. Each of these binomial random variables was obtained by summing m Bernoulli random variables, and we want to determine the maximum likelihood estimator for the p parameter of this distribution. By now, we should be familiar with the probability mass function for a binomial random variable with parameter m. We can thus insert this familiar expression into our expression for the likelihood as shown here. Now follows some straightforward algebra. We first rewrite the product as a product of two products as shown here. We can do this as the operation of multiplication of numbers has the commutative and associative properties. We can thus perform this series of multiplications in whatever order we like. Now notice that we can use the laws of logarithms to rewrite a product of exponentials as an exponential of a sum as shown here. To be clear, all we are using here is the fact that a to the power b times a to the power c is equal to a raised to the power b plus c. We are just doing these same operations with many more terms when we do it with product signs and sigma signs. Now notice that based on the definition of the sample mean, we can rewrite the sum of all the results as the number of results n multiplied by the value of the sample mean, x bar, as shown here. We thus started with an expression for the likelihood that looked pretty horrible, and through some relatively straightforward algebra, we arrived at something that looked far simpler. Recall that the objective here is to get an estimator for the p parameter of the distribution, and that the expression for the likelihood we have just arrived at is an expression for the probability of obtaining this particular result for the sample mean, this particular result x bar. Just as we did in the previous video, we will arrive at an expression for p by maximizing this probability, this likelihood. In other words, we are going to find the maximum likelihood estimator for the parameter p. There is one further trick that we can do before getting into the differentiation, however, which will make our life a bit easier. We can calculate and differentiate the logarithm of the likelihood rather than the likelihood itself. It is fine to do this as the logarithm is a monotonically increasing function. The maximum for the logarithm of a function is thus located in the same place as the maximum for the underlying function. We can thus find the maximum likelihood estimator by either differentiating the likelihood directly or by differentiating the logarithm of the likelihood. In what follows, we will differentiate the logarithm of the likelihood, as differentiating the logarithm of this function is a little easier in this case. We thus start by noting that the logarithm of the likelihood is given by the expression below. The most important thing to recall in deriving this expression is that log a to the b is equal to b log a. We now want to find the value of p that maximizes this log likelihood. We thus differentiate with respect to b. The first term here does not depend on p, so its derivative is thus 0. For the second term, we recall that the derivative of log p with respect to p is 1 over p, and thus this derivative is as shown here. For the final term, meanwhile, we note that the first part of this expression does not depend on p and will thus appear as a multiplicative factor. To differentiate the logarithm of 1 minus p, we use the chain rule with u equal to 1 minus p. du by dp is thus minus 1, and df by du is 1 over u, or 1 over 1 minus p. The final derivative of the logarithm of 1 minus p is thus du by dp multiplied by df by du, which is minus 1 times 1 over 1 minus p, which is then multiplied by the constant term that appears in this front of this expression, as is shown here. We thus arrive at the following expression for the derivative that must be 0 at the maximum of the function. Rearranging this expression gives the following. Notice that once the brackets are multiplied out here, there are factors of minus pn multiplied by x bar on both sides of the expression here, and that these factors thus cancel. With a little bit of rearranging, we thus arrive at an expression for our estimator of the p parameter. This estimator is equal to the sample mean for all the random variables divided by m, the number of random variables that were the number of Bernoulli random variables that were generated for each of the binomial random variables. In previous weeks, we have seen how some of the estimators that we obtain for the parameters of random variables are biased. When we use a biased estimator to determine the parameter of a distribution, we thus get an estimate for the parameter of the distribution that is inaccurate. With that in mind, we should thus always check for bias in the estimators that we derive using any method. As we have seen in previous weeks, we check for bias by calculating the expectation for the estimator. In this case, the estimator for the parameter p is the sample mean over m. To determine the expectation, we thus need to calculate the expectation shown here. We can simplify this expression by remembering that m is a scalar. A factor of m can thus be taken outside the expectation operator as shown here. We are thus left to calculate the expectation of the sample mean, which is the same as the expectation of the random variable from which the sample mean was computed. These random variables were all binomial random variables from a distribution with parameters p and m, however. The expectation on the numerator is thus m times p, which is the expectation of the underlying binomial random variable. We thus find that the factors of m in the numerator and denominator cancel out, and that our estimator for the parameter of the binomial random variable that was sampled is unbiased. Happy days. Notice that the estimator for the parameter of the random variable that we have just generated is itself a random variable. We thus might ask ourselves what probability distribution our estimator P is sampled from. We will come back to where this expression comes from in subsequent weeks, but for now I just want you to note that we can calculate the variance for the maximum likelihood estimator using the expression shown here. The so-called asymptotic variance for the maximum likelihood estimator for the parameter of a random variable is equal to 1 divided by minus the expectation of the second derivative of the log likelihood with respect to the parameter. Let's thus use this expression to calculate the asymptotic variance for the estimator of the p parameter of the binomial distribution which we have just determined. On previous slides, we have seen that the log likelihood for a sample mean x bar that is calculated by taking the sum of n binomial random variables is given by the expression shown here. Furthermore, we have seen that the first derivative of this function is the following. Differentiating this expression for the first derivative one further time with respect to p then gives the following expression for the second derivative. We now need to calculate the negative of the expectation of the second derivative to evaluate the denominator in our expression for the asymptotic variance. Before doing this however, notice that the only random things in the expression for the second derivative of the log likelihood are the factors of x bar. Everything else in this expression is a scalar constant and can thus be brought outside of the expectation operator. The negative of the expectation of the second derivative of the likelihood is thus given by the expression shown here. We now note that x bar is a sample mean that is calculated by adding together identical binomial random variables with parameters m and p. The expectation of this sample mean is thus the same as the expectation of the underlying binomial random variable, i.e. m multiplied by p. We thus arrive at the following expression for the expectation of interest. Bringing this over a common denominator then gives us the following, which we can insert into the expression for the asymptotic variance to give the following expression for the asymptotic variance of the maximum likelihood estimator of the parameter of the binomial random variable. Just in case anyone is wondering why this is not equal to the variance for a binomial random variable, np upon 1 minus p, recall that what we are calculating here is not the variance for the binomial random variable. This is the variance for the estimator of the parameter of the random variable. It is the variance of an estimator for the parameter p. Now notice that this estimate of p was calculated by taking the sample mean from n binomial random variables. This sample mean was then divided by the m parameter of the binomial random variable. I mentioned this as the expression for the estimator of p is an expression for the sample mean of n times m Bernoulli random variables. These are the n times n Bernoulli random variables that were generated to calculate all n of our binomial random variables. With that in mind, this expression for the variance makes sense. On the numerator, we have p multiplied by 1 minus p, which is the variance for a single Bernoulli random variable. This is then divided by n times m in order to give the variance for a sample mean computed from n times n independent and identical random variables with variance p times 1 minus p. In this case, by calculating the asymptotic variance, we have thus arrived at a result which we have seen, albeit by a different route. To summarize then, we have in this video explained how we can use likelihood maximization to find the parameters for many types of random variable. In doing so, we write the following expression for the likelihood of the result we have obtained. Alternatively, we can take logarithms of both sides of this expression and write the following expression for the log likelihood of the result that we have obtained. Once we have an expression for the likelihood of the result, or the log likelihood, we can differentiate the expression with respect to the parameter of interest and set this derivative to 0 in order to arrive at our expression for the maximum likelihood estimator of the parameter in the distribution. Whenever we arrive at a new estimator for the parameter of a distribution, we should check if that estimator is biased or not. Lastly, for maximum likelihood estimators in particular, we should calculate the asymptotic variance of the estimator using the expression shown here. The problems in the quiz and the exercises that follow will give you an opportunity to apply this method yourself. Good luck with those exercises, and thanks for your attention.